Swayam Prabha. Digital India. Educated India.
Let's move on with the hands-on session. So there are a couple of parts to this hands-on session. First is easiest first is just go to this website. I think most of you have already been there. If not, just go there, jarvis.nis.gov. Any problem getting there? If you are having problem getting there, it's probably the internet issues. So once you go there, please make an account if you can. So on the right hand side, there should be a login page. Let me see if I can just go from here. Can I? Yeah. I'm not super cumbersome with Chrome. Okay, so if I do this, you see there's a login sign up. Click sign up. Account block, too many attempts. I didn't even try much. Same for you guys? Okay, I don't know. Somebody's blocking the IP address. Anyway, it's not necessary for this tutorial to have total access. What I do want to point it out is once you visit this, there's a section called tutorials. You see that? Tutorials. Click on tutorials, and in tutorials, the first one is JARVIS-Tools-Notebooks. So you want to click on this. This leads to you this GitHub page. Yeah. Do all of you have GitHub accounts? Yeah. Anyone doesn't have GitHub accounts? No. So I mean, if you work in computational material science, there is a joke that people don't even see your Google Scholar profile or how many papers you publish. They see your Google GitHub profile. Based on that, you get a job nowadays. So it's good to have a GitHub account. Anyways. Don't feel pressure to make one, just saying. Okay, so we went there, and then, so you see that here we have what is Jarvis tools, introduction, what is the basics, electronic structure, force field, AI, ML, quantum computation and stuff. So let's call the basics B, I think, electronic structure ES, force field FF, AI, ML. And that is the abbreviation we will be using for this B, B1, B2, B4 and so on. Okay. So we went there, and according to this guide, first is HPC basics. So again, many of you might be familiar with this Linux system and stuff, but I still, because we want to put everyone on the board, we have some basic introduction to HPC. So this is from the TAC, Texas Advanced Computing Guide. You'll see there are like what is storage and stuff, but I want to show you the commands. Let me go next. Yeah, Linux commands. So for example, this command like pwd, present working directory, ls list file, mkdir. So yeah, if you go to this, were you able to get to this? So click on basics 1. Let me click one more time. So you went there, an introduction to high performance. Yeah. Of course. Better? You could, yeah. So yeah, I think it's the 5th page or something where we have the commands. So this is especially for people who have never used Linux, and honestly, some people are scared of Linux when they think of just to see file, you have to do a command, they get scared. So don't get scared, it's super friendly, super easy to use. If you want to create folders, if you want to manipulate files, there's a touch, rm, vi, nano, all these commands. And this is nice, I think, introduction to kind of HPC system. And if you are new to this, it would take probably a couple of days to get familiar with HPC, but super easy. Don't get scared with this. And this is a nice, I could find these are nice examples. And especially if you are working on computational material science, materials informatics, you might at some point interact with HPC system, and you might need allocation. So this tag also gives computational allocation. I don't know internationally, probably it does. Let's take a look. So I think IIT also have some sort of cluster you can get an account. So good to be familiar with some of the basics of the. So there is no hands-on session per se, but just to be familiar with this. The second notebook is more important. Any question there in HPC part? Good. So the second one is B2 Python Beginner Notebook. So we will click on this one and open in a new tab. Let me kill these tabs and make it screen a little bigger. So Python for really beginners, and yeah, this might be super easy for people who are too familiar with this, but please bear with me. So first thing, any programming language you learn how to use print hello world, right? And the way it works, the Google Colab notebook is kind of a Jupyter notebook, but it's running on the Google platform. And who this D is, I don't even know. Anywho, yes, so you have to sign up with your Gmail. You must have a Gmail account, and you click on this play button. Then it asks you run anyway, and then it allocates some computational resource for you connecting. Right, it will probably take a few seconds. There you go. Now we have RAM. We have 12 GB RAM for free, 100 GB disk for free, right? Free in the sense to a certain extent. And if you want more, they have a Colab Pro and stuff. Anyhow, so print hello world. Please raise your hand if you made this. I want to see all of the hands. Else I'm not moving on. Okay, I can wait for a few seconds. I see that 3-4 hands are still waiting. So remember, you still need Gmail account to access this. So the print is a function. Hello world is under quote and quotes, it will become a string. For example, if I put hello and there is no quote, oh shoot, what did I do? Put this and there is only this, you will see it will give error. See, why does it give error? First of all, there is no comma between variable, and then world is now considered as a variable, not a string, so it will give you error. Okay. Okay, so I'm assuming most of you got hello world. Okay, so I'm going to move on. So the next one is very simple. Remember, I talked about the type of variable: integer, float, characters. So here 2 is integer. If I make it 2.0, let's see what it becomes. Now it becomes float. How many bytes are there in a floating number? Can anybody tell me? 32-bit. It can be 32-bit, it can be 64-bit, 64, yes. 8, yeah, good. So you should know that, because again, in some of the materials informatics, they will try to store the 64-bit into 8-bit. So there's a very interesting thing, I just read it. Suppose you have neural network weights like 3.11, you have a matrix 3.11, 3.22, 1.6, blah, blah, blah. What I would do is, I will take the maximum number or the sum of this matrix element and divide this by the this sum, and then matrix divided by that number, and then whatever the integer part, I'll store that and throw out the float part. Okay, and in this way I could save a lot of memory, because now it's stored, but stored in an integer format. So each is 8-bit, and that is how all this LLM quantization. This is called quantization. That's how all this LLM works in terms of float versus integer. Now you want to revert back, you just multiply this denominator with all these numbers and get approximate floating number. Question? You lose some accuracy, yes. But again, computational expense, because if you want to host this model on cloud, you have to pay a lot of money. So people who are smart, I mean, this is just in one example. There are many methods like Q4KM, QKM. There are many algorithms how to store this in an integer format without losing information. But anyways, so types of variables, very interesting. Sum, division and stuff. Exercise. I was told that you guys have some credit for this, at least some of you. So remember, whenever there is an exercise, what you do is you just comment it out. This third quote unquote is called comment in Python. Take it out and run it, and it will give probably error. Yeah. So yes. So it will give you 0, 1 over 3, but round up to like 2 digits. I'm sorry, it should be like here. .33, round up to 3 digits, 0.333, and so on. So this is rounding numbers. Again, you can have string addition, my awesome code, for example, and there are exercises. You cannot add one integer type or float type to string. So if I tried this, print a plus b, it will probably give error. Yes, so you cannot add this. But if you have string casting is possible, so you can convert 2 from integer to put something called str, and it becomes string. Then it becomes code 2, code space here, and then 2, right? So you can have string casting. Remember, we talked about for loop. You want to perform square operations. So you will go over entire array 1, 2, 3, 4, 5 for loop and do. This is multiplication of 2. Just multiply by 2, and this is the for loop. You can calculate, for example, percentage operator to get like even number and so on. If you want to calculate mean, max, minimal, medium, all those statistical inference thing, you can get it using NumPy. We talked about dictionary, right? So I love Marvel movies. So here are a few Marvel movies: Iron Man, Spider-Man, some other favorite movie like Godfather, Lord of the Rings. So suppose I want to have all the keys of this dictionary. So these are called a.keys. That will be Marvel movies and other favorite movies, and the values are what is after the colon. So Iron Man, Spider-Man, and the Godfather, and so on, right? So these are, is this part clear? What is keys and what is values? Any questions? It's very important to learn this concept. All right, so keys, values, and again, as I said, you can access the values of a key of a key. So a other favorite movie, and if there was a dictionary, you can ask for that as well. Now you can update this with some thriller movies like Silence of Lambs, Bourne Identity, Inception, whatever, right? Now you can read-write this JSON file. So you want to store this JSON file. So there is a library called JSON. So anytime you see this pink color, import, that's basically a library. So you can open a file called fopen in a write mode, dump that data, like A was a dictionary or something, and store it. Similarly, you can read that data. So here we are storing the data, reading the data, and then printing the data. So what happened here? So it was casted in a string format. The string format was casted in a ASCII byte format, stored in a file, and then it decodes it, unbytes it, and it displays here, right? So that's what the process is. You can also know about plotting the data. So I think Excel is probably the most popular plotting software. But in Python also allows a lot of plotting, sophisticated plotting. So here we use very simple x and y data. We try to plot it, and there are different signs like with O versus with caret or upper triangles and so on. Now we talk about functions, def. So we talk about this functions, which is, for example, adding two numbers. It's like a calculator. And for large data set, there is a library called pandas, similar to the cute animal pandas. So you can import in a function a library and call it a PD. So you can call it as PD, I don't know, P also. You can call it anything you like. Import that, and then it's right now it's reading from this link. This link is an online link, reading the column 0. You can see if I paste it here. That's a good thing. You don't have to download the data, just put it from the link. Okay, it's kind of downloaded here. So this is one way to interact with pandas. Can you please raise, yes? Bigger? Oh, sure, that's a good point. Okay, thank you. So, and how many of you have used pandas before? Please raise your hand. Okay, so most of you have heard or used it. So pandas has some nice functions like called describe. So it can give you the mean, median, standard deviation, and so on. What are the columns? What are the rows? So any panda is like a Excel sheet, right? So rows and columns. You can plot in pandas, like scatter plot, line plot, and stuff. There are some exercise as well. So yeah, this is very beginner level of programming notebooks. So remember, whenever you are using Google Colab notebooks, you are given certain amount of time limit. So whenever you are done with this, go to runtime and go do disconnect and delete runtime when you are done. Else you'll be wasting resources. Okay. So make sure you do that. So how many of us were able to completely go through the notebook? Please raise your hand. Most of you, very good. We can wait for a couple of minutes if you want before we go to the next one. We still have time. Yeah, after do that, just disconnect it. Yeah, so what they are doing is they are trying to allocate a CPU for you, and the maximum amount is 10 hours per day per Gmail account. 10 hours per account per Gmail, per Gmail account per day. So yeah, you don't want to run it out. I mean, you won't run it out, but sometimes we do. Yeah. And something I didn't show you, you can also use like GPU and stuff. So you can use different type of GPUs, TPUs. If one of the exercises was like compare CPU versus GPU code. There is some example there. Maybe we'll try to go through it. So we can compare the same notebook where you have the GPU on and GPU off, and you can compare the timing and stuff. Okay. So this is called Colab notebook. Because this thing takes so annoying that you have to disconnect and all this kind of thing. So I wrote something just because I was so annoyed. Something called SLMat. It's a project. I did not talk about it, but this is a browser-based computing. So it's called serverless. There is no servers. So here you will see that this can work directly on browser. I don't know why this did not open, but let's see. Yes, there you go. So this one will be working on your browser directly. You don't. It's called SLMat, Serverless Material Design Toolkit. SLMat GitHub. And then you can do the same example that we did. This is for ASE scaling, but there are some other beginner Python notebook as well. And this is very useful for something like when you don't have to manage a server, right? Server management is a pain. If you work with material informatics, one of the really painful things is managing server, and it costs a lot of money actually to host on a server. So if you can host something like this, which runs on the browser. So what it does is you can convert. It's called web assembly language. We won't go into this, but it converts this Python script to JavaScript internally, and then you can run the JavaScript on the web browser, right? So it does automatically inside it. Anyway, it was not part of, what is it? No library installation needed. It just everything is there. So the library is called Pyodide, which is already comes with when you install this. When you click on one of the links. So like Python for a basic example we did. This is something broken here, I feel like. But some others like visualizing atoms, let's see. Yeah, same thing, you can visualize atom and stuff. So it cannot install a lot of softwares. It can only do certain softwares right now because again you have to convert this Python to JavaScript and so on. So we are working on improving that. But currently in our hands-on session we'll be using Colab notebooks. But all right, okay, too much tangential trajectory. So let's go to the B4, which is silicon. Yes. your laptop, yeah. So your laptop has certain RAM, right? So it can access that RAM directly, and then you don't have to install software again and again. You don't have to disconnect, and it's running locally, so you don't have to pay for it. But
what is the system requirement?
system requirement, like minimum system requirement, any you can run on a phone. Yeah, yeah. I mean nowadays phones are so powerful. It's like so much RAM and stuff. You can, but again, if you want to do a lot of intensive calculation, it will not work because again RAM limitations. So there is a business idea too. Like something works, you can run there. Then if not, you put to some company thing and they'll pay for this. But those are business ideas in material science. Okay, so we did B1, we did B2, we want to do B4 now. B4 is silicon atomic structure analysis. Open a new tab. Any question up to B2, please raise your hand or feel free to stop me. Okay, good. So why do I want to start with silicon? Silicon is one of the most popular material, and I do feel like anytime I do any modeling, whether it's DFT, MD, machine learning, quantum computation, whatever you think of, my favorite thing is start with something really basic like silicon, and like go through the details of this. So in this example, we will see how to construct atomic structure for silicon, how to plot X-ray diffraction, radial distribution function, how to create a surface vacancy, interface, and so on in this exercise. So be ready for this. So anytime in Colab, you have to do this pip install. So pip is a way to install softwares. So we are installing Jarvis tools here, which is a software we developed. Again, run anyway. Quiet. -Q is quiet because else it will write bunch of different things which I find very annoying. So, but you can put minus, you can take out -Q as well if you like. So currently we are using 0.911 gigabyte only for this installation, you can see, and 35 GB RAM. I don't know where this 35 GB is, but okay. Now we successfully install this Jarvis tool, SPGLib, and ESC library. These library can be used to construct atomic structure. Let me see what description I write. A crystal structure is defined by a lattice matrix atomic. So we heard about that in the previous session. An example, let's create a silicon atomic structure. We need to import atoms class. So we import this. So remember the pink thing? Pink thing is a function. So we are calling jarvis.core.atoms. So Jarvis has a function versus function, and atoms is an object. Remember we talked about object-oriented programming. So in this we need three things. Box or lattice matrix is a 3x3 matrix in XYZ. It is a coordinate, XYZ coordinate, and the element type like silicon or something. And then you give this to this template called lattice matrix equals to box, coordinates equals to coordinates, elements equals to elements, and it will be able to create an atomic structure called silicon. Now when you have silicon, you can also visualize it using something like ASC. And you can, on the Colab, you can visualize how the atomic structure looks like, make it small, big, or whatever. Now this was the primitive cell. You can also get the conventional atomic structure. Click on this, and it looks nicer, right? Nice rectangular shell and stuff. It's conventional atoms. Now once you have this, you can calculate something like radial distribution function. So in radial distribution function is a signature of that material. And you take, for example, an atom and make a circle and take a small ring and another ring and another ring and count how many atoms are there and divide by the volume of the cell, and that gives you something called radial distribution function. So for this, as you can see, we're getting all the neighbors of each atom up to 10 angstrom distance and adding to an array using a for loop called distance. Then we use the NumPy library and make a histogram, right? It's like a bin kind of thing between 0.1 to 10 angstrom. So we have pockets of 0.1 angstrom, 0.2 angstrom, 0.3 angstrom, up to 10 angstrom, and we are trying to count how many atoms are there in each bins. That's what this code is doing. and then we calculate the volume and normalize this, because if we have bigger and bigger cells, it might scale, right? So you want to normalize with the volume, and that will give you the radial distribution function. So what it says, this is called first neighbor at 2.1 angstrom, second neighbor, third neighbor, fourth neighbor, right? Yeah, this for entire silicon system, and including the periodic boundary conditions. No, I mean you have one atom, but you also another cell of second atom, third atom, fourth atom, and keep in.
What is for one atom and their corresponding neighbor, right? Not for the whole atom we are considering. Each time.
Single crystal is called single crystal.
This is for single crystal, not just for one atom. Let me try to explain this. So you have one atom here, right? And then one atom here, one atom here, one atom here, so on. My drawing is horrible. So you take a radius here. Within this there is no atom there, right? So there is blank up to 2 angstrom. There is a blank. Suddenly there is another atom here. Then again there is a blank. So that's what it's representing. And you count this for all possible up to 10 angstrom. So you make, suppose the unit cell is like 5 angstrom, and you take up to 10 angstrom. Another cell, another cell, another cell in 3D, and count all the possible atoms, right?
So the atom in the center, this plot is for it, for this, right?
Yeah.
Not for all different.
Well, because they are all all the same, because in silicon case all of them are symmetrically same in a way. So it kind of, for if you get it for this, you can also get it for this, kind of same thing, symmetrically equivalent. Right. If you have like aluminum oxide, then you will have a pair distribution for aluminum, oxygen, aluminum, aluminum, oxygen, aluminum, and so on. Right? You can break it down. So this actually for silicon, silicon, you can say. And as I said, because it's a class, lot of functions comes inbuilt with it. Although we did not code volume, how to get volume, how to get density, how to get space group, it automatically gets, is encoded in that atoms class, and you can get all of this for free. Atomic number, center of mass. See, we did not code for this, but we are getting this for free. You can also print this system. You can see this is the repeat unit, direct coordinates. So this is the 3 by 3 matrix for the repeat units, 2 silicon atoms. Direct means fractional coordinates, that is coordinates between 0 to 1 only. So there are 2 types of coordinate system, Cartesian coordinate and fractional coordinates. Fractional coordinates can be from 0 to 1 only, and or direct coordinates, and the Cartesian coordinates can be actual numbers like 500 or something, but it can be interchangeably converted because you know the lattice parameters. Just divide by the lattice parameters and becomes the fractional coordinates. Yeah, so this is 0, 0, 0 first atom, and 0.25, 0.25, 0.25 second atom. Yes, this is X, Y, Z position. Yeah. So that's how you make the tetrahedra. Remember the famous. So this is 0, 0, 0, and this is 0.25, 0.25, 0.25. And because they are symmetrically distinct, symmetrically similar, you have to do only 2 atoms. And by symmetry, they will replicate itself. Symmetry is very interesting topic. I didn't have chance to talk about this, but maybe we can discuss a little bit. But so silicon is a object, again, atomic structure with a dictionary of lattice matrix elements and coordinates, and for free you can get the ABC lattice parameters, angles, and you can associate or save properties like velocity of the atoms and stuff. What are you doing now? So this is just putting into a dictionary format, loading from dictionary format and stuff. Sometimes we need supercells. So we have a unit cell, you want to replicate it multiple times, like 2 by 2 by 2 times. You can do that, and you will say that you will observe that the density of the supercell and density of the primitive cell has to be the same, because you just replicated this, just a sanity check. So it is equals. So this means double equals is basically a conditional statement. So it's checking whether this density, which is, what is the value? What's the silicon density? 2.33 gram per centimeter cube is equals in for both supercell and the unit cell. Some space group analysis. So we can import the space group 3D and get, for example, the number of atoms in the conventional cell of silicon, Wyckoff multiplicity. Sorry about this spelling mistake, but Wyckoff is basically a very interesting thing in crystallography, where basically it says the letters A, B, C, D, E. You might have seen that. So it's basically if you put an atom, how many times it will be automatically replicated based on symmetry. So if it's just 1, I believe it's A equals to 1, B is 2, C is 3, and so on. So I think max is up to G. So so here you can see it's B, right? So you can get the Wyckoff multiplicity. Sometimes there are systems such as aluminum oxide. So their oxygen is oxygen, but they have 2 types of multiplicity. One is, I think, B and one is C. So when you do experiments, you can actually do something like UPS measurement and see which oxygen is participating in a reaction versus the other. So you can calculate that or do an experiment. What we are doing here. So you can load also these structures from something called POSCAR file. It's a way to represent in a VAS format, and you can just literally post it there in this 3 colon quote 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 string quote quote quote, and then read from string, and it will get the same behavior. You can visualize it similarly. Vacancies. So we are talking about defects. So we can represent vacancy structures with this format. And
POSCAR acronym for something?
I don't know, the positional file for Cartesian coordinate or something like this. But somehow this software VAS was too obsessed with cars. So in car, pod car, whatever car. But yeah, you can also read from CIF file, XYZ file, PDB file is good for proteins. This is a vacancy structure. So you have taken the silicon's atomic structure that we created previously, and we were asking for generate a 10 angstrom cell and make a defect, like one defect. So it should be, so we have 2 atoms, and we are getting 53 atoms. So can somebody tell me what is the supercell we used? Maybe too difficult. Anyways, ignore this. Too difficult. My question was like, what's a supercell was used? What's like 2 by 2 by 2, 2 by 3 by 3? What's a supercell we used to get 53 atoms in a defective cell? Maybe it's too difficult. It's okay. You can do this exercise. This can be a good exercise. So we ask you to generate a 10 angstrom cell, and then take one atom out randomly, and there are 53 atoms. And similarly, you can calculate, create surface, which is a area defect. And here we are asking Miller index to be 111, 3 layers, 18 angstrom vacuum. So we basically have a system like this, where there is a material here, and there is a vacuum. These are vacuum. And when there is a vacuum in a periodic cell, we call it a surface. Okay, so that's what we're trying to create here. And this is you can see there are 24 atoms in this surface 111. You can visualize it. It's a little weird to see, but let's see. Anyways, it looks like something like this vacuum thing, which I talked about. Sometimes you need to make interfaces. So here is a good condition, just silicon on silicon. So there is something called ZSL generator, so which is useful for something called Zur algorithm. I won't talk about this, but suppose you have a silicon and gallium arsenide and put on top of each other, which have mismatch in lattice parameters. So the old-fashioned way was take the LCM, lowest common multiplier. What is it called? LCM. Remember those things? So suppose it's lowest constant. So it's a 5 angstrom lattice constant. One is 4 angstrom. So what you can do is make 20 angstrom, both of them, and then both will fit, right? So that is one way, but this you can see there will be, you have to make 20 angstrom for both of them. That will make the system too large, right? It's too difficult to simulate. So Zur in 1986 or something, if I remember, what he said is, suppose you have a cell here like this, and suppose you have another cell like this. So he said, what's the common cell I can get, something like this, which will be close enough. So he wrote an algorithm called ZSL algorithm in 1980s. I can't imagine how they did without that much sophisticated computer programming and stuff. It's really, really fantastic what he did. So he wrote a code. You don't have to do LCM, but it will find a primitive cell in each surfaces and try to put it together. So it will try to do this kind of snapshot, 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 all the possible chunks, and all the possible chunks here, all the possible chunks here, and calculates the lattice mismatch. And then whichever the lowest, it will give you that, and then you just make a sandwich, and that becomes the interface. Again, there are certain companies like Quantum ATK and stuff. There are some softwares. We make a business model out of this, how to make interfaces. And it's like software price is like $10,000. So similarly, you can do neighbor analysis. So suppose there is a person here. What's his first neighbor, second neighbor, third neighbor? What's the angle interaction? I should give a homework like this. From you, make a radial basis function and calculate the radial basis function around you. So if this was a dedicated class, maybe I will give you an exercise. But here we'll just do for atoms. We have a function called neighbor analysis, which gets you the radial distribution functions, angle distribution function up to first order, angle distribution up to second, dihedral distribution, and we can plot it. And these are also very distinct features or signatures of that material. So silicon, no, not silicon is not a good example. Maybe aluminum. So aluminum, if you have in HCP phase and FCC phase, right? And if you calculate the RDF, they will look very similar. But when you calculate angle distribution function, it will start looking different because they have different angles. So that's why we see that RDF is not necessary as a signature in a way to distinguish materials from one another. So when we will do like materials fingerprints and descriptors, we'll find what's the best way to distinguish from each other, and then we try to pad this RDF, ADF, DDF to kind of make it as unique as possible. And the more unique features you make, the computers will understand this kind of what's different and make better predictions in a way. So that's why I think it's important to understand RDF, ADF, DDF, and so on. X-ray diffraction. I'm really fascinated by X-ray diffraction. I think it's one out of all the material science experiments, I think 90% of the experimental data come from X-ray diffraction. Why? Because it's super easy to use, right? And I won't have time too much to details to talk about what goes in the XRD. But what happens is, because I'm so fascinated about this, let me talk about for a minute. So if you have a planes of atoms like this, and then you have a ray, let's try to draw this. So these are incident ray, and incident ray, reflected ray, incident ray, reflected ray, and then you have a wave, right? It's a wave-like behavior, and there is another wave-like behavior here. So two waves, and they are in phase. What do you mean in phase? They look similar, right? But here, this wave travel an extra distance, this one and this one, right? And this, if you know the wavelength of the light, you can do some trigonometry, like if you call this angle at theta or something, and this will be theta, and this will be theta, and so on. You can calculate what's this one based on the sine theta, and so there was a famous equation called n lambda 2d sine theta. Am I writing it right? I think I'm so, yeah. So this is a Bragg's law. So in computationally, what we do is, suppose we have planes of atoms, right, like this, in an infinite lattice, and then you create all the possible HKL. Okay, forget about atoms at all. Now you have up to 3 Miller index, up to 3. Okay, so how many Miller index can you create? 333, 321, 311, 3 minus 11, 112, 113, all the possible combinations. And if you know this, you can calculate the interlayer distance. D is equals to 1 over h square, k square, l square, all those things. Now you calculate that, and then you will see which of them matches the interatomic distances. Wherever it matches, there will be peak there in X-ray diffraction, right? And now how much the peak will be depends on the atoms, and that is in a dictionary, already defined dictionary for that atom, characteristic element and stuff. And you do this kind of for a average for entire material, and that gives you powder X-ray diffraction pattern. So here is the powder X-ray diffraction of silicon. So one of the way to do machine learning for atomic system is just do X-ray diffraction pattern as a fingerprint and predict property like band gap, formation energy, and so on. So there is a very interesting paper I saw. It's called XRD is all you need. A very interesting paper. You should take a look on this. So according to them, this paper, if you have X-ray diffraction descriptor, you don't need anything else in terms of machine learning. Okay, so and there are certain things about, these are very spiky, but in experiment you have certain noise and stuff, so you want to add some noise or Gaussian peaks and stuff to get profile. So I will not go details of this, but just smoothing of the data, that's what it's doing. Now and especially if you are using Jarvis tool, there are certain features to get descriptors. Remember we talked about it. So what are descriptors? You take RDF, ADF, DDF and pad it together. So that's a structural fingerprint, right? Similarly, you can have chemical fingerprint. Suppose you have silicon, molybdenum, aluminum. Take the average of their electronegativity. That's one number, right? So that is a chemical fingerprint. So if you take chemical fingerprint, structural fingerprint, it kind of becomes a unique fingerprint of that material. So that's what this program is doing right now. It's trying to get both the chemical descriptor and the structural descriptor. It gets 1500 such descriptors, 1500, a lot of descriptors. And another way to get a unique fingerprint is called graph. Okay, so we will come to this later when we talk about deep learning. Again, we are just learning silicon here. Okay, so a graph is suppose you make a graph in Excel sheet. What do we have? We have few points and a connecting thing. So these dots are called nodes, and this connection is called edges. Okay, so a graph is a collection of nodes and edges. So these nodes can have node attributes like electronegativity, boiling point of the atom, I don't know, atomic number and stuff, to distinguish from one node to another node, suppose silicon and oxygen. Now there is an edge feature like bond distances is an edge feature. So if you know this, then you can distinguish one material from another too. So there are certain tools we developed which can take the silicon atomic structure and directly give you the graph. But again, when you give you graph, we talked about it, it gives you the nodes and the edges, bond distance. But we are material scientists, we are not just data scientists. What do we know from material sciences? Material science, what matters is angles and dihedrals too. So how do you get the angles and dihedrals? So what we proposed is, if we have a graph, then and we have edges, now we consider another graph where the edges are the nodes and the edge pairs are the new edges. I know it's a little confusing, but in this way you can get angles, right? So this is called line graph, LG. So you can go get both graph and line graph from this. So for silicon atoms, you can see, I don't know what happened, oh, it's still installing. So you will see there are two nodes, because we have two nodes in the primitive cell, 56 bonds in the graph, but in the line graph we have now 56 nodes. What edges before become the node here, and 1520 edges of the new graph which has angles and stuff. So that's how you can get, and then you can also associate the atom feature like atomic number and all this kind of features to distinguish from one another. So yeah, this was the story of silicon. So I'm pretty sure, yeah, there are questions. Yeah, we put chemicals. So right now we have, I think, atomic number only as chemical features, but you can put something else too. Yeah. So yeah, let's get the graph. And you can see there are two nodes, 56 edges as we are talking about it atom features. So you can have only one atom feature like atomic number, but here we have 92 such features for and so on. And yeah, so this was the story of silicon. I think I gave exercise. Similar to silicon, make surface vacancy structure RDF XRD plot for aluminum and aluminum oxide. Find the atomic structures for, or postcard from Jarvis DFT. So we saw the Jarvis DFT, go there, click on aluminum oxygen, get aluminum oxide, and where there was a postcard, remember there was a postcard somewhere here? Here, yeah. Just paste this, whatever data there here, and do the same exercise. Calculate the vacancies, surfaces, and whoever have some points for this, they'll have to do this and submit this notebook, I believe, right? Yeah. So for then, that's how I recommend the the homeworks nowadays, because I don't have time to go through each line by line and stuff. So once you have the output, I can just take a look and see whether it's right or wrong. Okay. So now we are done with this notebook. Any questions? Any burning questions? Yes.
So in XRD, how do you get the intensity? Like we got how to get
the positions. Good question. So there is a formula like F HKL equals to sum of F HKL small HKL e to power I HX KY LZ, and this F small this, these called structure factors. This structure factor for each atom is kind of very characteristics and it's available in databases. And so once you have the HKL indexes and you have this one, you can calculate the intensity of that HKL for that atom. Yeah. All right. So where were we? Okay. Any other question? I like the question. Very, very, very good questions so far. But not so good questions are also welcome. It's okay. Atomistic graph? Yeah, sure. Yeah. Right. So chemical fingerprints usually deal with Euclidean geometry. Let me talk about what is Euclidean geometry and non-Euclidean geometry. So Euclidean geometry is a grid. So suppose I want to represent molybdisulfide or something. So I will have electronegativity, atomic number, boiling point, I don't know what to represent this, B or something. And then there will be some value, and then I take an average of this. This is one fingerprint of that material, right? You can see it's working on a structured format, but the coordinates of an atom is not in a structured format. And an atom can be here, atom can be here, atom can be here, atom can be here. So this is called non-Euclidean geometry, where it's not based on such a structured grid. And to represent this non-structured data, graphs are used. So again, as we said, it's represented by the nodes. These are the nodes. It can be atoms. It can be atoms like MO, S, S, S. It can be Twitter or Instagram accounts. So this is your friend. This is its friend. So how does if somebody some person like this reel, how does it affect you? There is also a node and edges, right? You can have a model for that. Like galaxies, stars, you can represent in a non-Euclidean geometry, right? So you can represent, for example, you as if again Twitter example, your age, your ethnicity, your color, whatever, and it should have an interaction with this. Probably same age, same I don't know, same genre. People will like that reel and stuff. So this way we can have the interaction. So this is the node feature, and for a material it can be like electronegativity, atomic number, boiling point, whatever. Recently we found just atomic number is a good descriptor, just atomic number from 1 to 100. That's it. Now the edges are the bonds, right? So this Rij. So these are the bonds. So this is fine for graph. Now suppose you have silicon oxide. I don't know what I'm drawing. Silicon oxide. So these are the nodes, and this is called a graph, right? But for a line graph, what will happen? I'll consider this, which was edge, to be now a new node, okay, and this as another edge, this one as another nodes become edge, and so on, all the possible combination, and the edges now becomes the triplets. It's a 3-body interaction now, because the edges are the nodes of the previous graph. So we can capture this angle now, right? So if these are nodes now, the feature of edge is the angle. Does it make sense? Yeah, slightly. Yeah, I know it takes some time to grasp this, but it's and the thing is, the good thing about this is very parallelizable. Like you can take a graph of a line graph multiple level very efficiently, and there are some sparse library, sparse C++ library which can tackle this kind of matrix multiplication. There's a sparse matrix algebra. There's a field there in linear algebra, so which can tackle it very efficiently, and that's why it becomes very popular. But yeah, that's how we represent graph. Please.
Reason why this graph concept has come about? Like, due to computation purpose only, or to make new kind of descriptors that capture all the things at once?
Yeah, so I believe the first graph neural network model come from Google, I think DeepMind or something, if I remember. So they were working with descriptor like fingerprints, but they reached a bottleneck. They were not able to get certain accuracy. So what they did is just tried out graph, and it works phenomenally well. So everybody now use graph. People still use fingerprints, but I feel like most of the people who have a lot of data, more than 500 or 1,000, they will tend to use graph for atomistic systems. If you have less than 500,000 data, I will still use fingerprints. Yeah.
So it is started in material science only or some other field? Like
Me?
graph networks?
Oh, graph networks? Graph networks are computer science, totally computer science. So I think its first one was, I have seen the paper on citation network. You know Google Scholar citation? So if you are a co-author of some co-author who cites to what, who is the first co-author, who is the second co-author, it's a good computer science problem. So suddenly some people say, oh, I can maybe use it for chemistry, and it worked out very nicely. So you never know. Graphs have been there for a long time. Yeah, non-Euclidean geometry and stuff. If you study about non-Euclidean geometry, there's a graph is a chapter, graph theory. All right. How are you doing with time? So we started at 11:30, right? So we still have 30 minutes, I believe. Yes. Please go ahead. Which one? In this notebook?
Yeah, get an atomistic graph for that. Is there equivalent for a specific version?
Oh, there is a specific version of DGL. This one, right? Yeah. So somehow this Colab doesn't work with latest version of DGL. So I had to pin the version called 2.1.
It is asking the latest version.
Oh, for you it's asking the latest version.
Yes, it says it's not compatible with 2.4.0 and requires 2.55.
Interesting. What I would do is, it worked for me, of course, here, but if I don't know why magically it's not working, so we will just try this 2 or something. Try this, maybe it will work. The version control is a big pain. I was talking about it. Remember the PI testing and stuff? This is where it's very important. Sometimes people upgrade software and it's not compatible. Oh, what did I do? Still we have exclamation point mark. So anytime you do exclamation mark, it becomes an executable. So here it will try to install some latest version. Oh, again I disconnected, so it won't work. But you can try just ignore the rest of the part, see what happens. Like take this part out, pip install DGL. If it gives you conflict, then it will give you the latest DGL version. But don't worry, we'll have some exercises with this later. This is just an example. So when we do the graph neural network training and stuff, so we'll show how to install with Conda and pip in a compatible format, and how to do actually a neural network training from this later. Yeah, this is just the beginning of that. So we did. Oh, we are okay. We are too slow. So to speed up a little bit. So 7 is ES1, electronic structure data, or maybe you should start with ES29 first. ES29, which is run GPaw on Google Colab. Get that? So this is how you run DFT calculation on Google Colab using a software called GPaw. There is also an example using Quantum Espresso somewhere there. So GPaw is a software code written by somewhere in Denmark. So we will first install is using something called apt install. It's a command in Linux, and pip install GPaw. These are all dependency of this software. Anybody feeling lost because of this jargon thing? I'm saying gibberish, little bit, yes. So yeah, apt install is a command, like you know how we do. What's the equivalent in Windows? I don't even know. Like you just download software and just click .exe file and stuff. The equivalent is apt install. Huh? Which one? In Windows also? Yeah. But the apt install. Apt, that's a totally Linux thing, right? Yeah. Windows has something called PowerShell. I don't know anybody else does this. It's a command line thing. Choco? Okay. I don't know, maybe. Something in Windows, yeah. So I mean, I think most of the OS has this. I think in Mac it's Brew Tap. It's called Brew Tap. Anybody has Mac, they will know. So same kind of idea, but you have to have certain dependencies, else this program won't install. It will take few minutes to install. Okay, it's done now. So you just want to see whether it installs successfully. So you call it GPaw test. GPaw stands for projected augmented wave, and G is I think the G vector. I think remember we talked about A1, A2, A3, and G vectors in the reciprocal space. I think it comes from there. GPaw info is basically giving you all the software dependencies, and here we will simulate aluminum. Somehow I love aluminum because it's a very good system. Single atom in the cell, small unit cell. So we had this again this postcard format where this is just the name of the system. I call it my system. You can call it your system, whatever you like. One is a scaling factor. It's a 3x3 matrix. Remember we talked about it. A1, A2, A3, and so on. The atomic types, fractional coordinate. You don't even need this one. Just 0, 0, 0 x, y, z coordinates in fractional coordinates. Then we talked about it. We can get the primitive cell with 1 atom. We can talk about it conventional cell with 4 atoms. You can visualize the atomic structure makes sense. So here we are doing 3x3 cell. Now this part we talked about this basis set, exchange correlation, k point and stuff. So this is where it comes into play. So we are using plane wave basis set with 500 EV cutoff, exchange correlation PBE, Purdue, Burke, E is Eisenhower or something. I forget the third one is difficult. I have met John Purdue, I have met Burke, but I have not met this guy E. He's somewhere in Canada. John Purdue is an amazing guy to talk to if you ever meet him. So k points is also the grid we are trying to solve. So usually what we do is we do 2, 2, 2, 3, 3, 3, 6, 6, 6, 10, 10, 10 and see where the energy converges. And where it converges, that is the optimal k point we should use. So in this calculator we are using GPaw software, and it's called setting the calculator. So just whatever we calc, we made it here. And then there is something called BFGS algorithm. It's also scientists of 4 people, 4 scientists' name. I don't remember this one. So what we are trying to do is optimize the lattice parameters and atomic position in a way the maximum force on atom is less than 0.01 eV per angstrom. That's what it's trying to say. So we'll try to do this one. It's actually very, very fast. Somehow this software has not been very popular, but I think it's very potential software. Okay, so you see it's trying to optimize 0.04 not converged, 0.02 not converged, 000 converged. So here it will stop it, and this is the equilibrium energy. Again, you see this trying to minimize the energy, and you can get the potential energy, you can get the forces. 10 to the minus 3 is minus 33 is very small forces. Now what is it? Now we can use energy force to make force fields. Yeah. So suppose you do this on many systems, and then you can get the energy force data, and then represent atomic structure with graph or descriptor, and then you can do this training to get something called machine learning force field. We will try to do this for one of the exercises, I think third or fourth day. You can plot the electron density, the electron density of states. So what is it? So you basically remember we did the histogram of bonds in the RDF. Consider them doing something for electrons. That's the density, electron density of states. So here we are showing that this is filled, this is unfilled, which we call what valence band, conduction band, right? And in metals they kind of overlap. Remember we read this in whatever high school class or something. And we can calculate electronic band structure. So band structure is a peculiar phenomenon in quantum mechanics, where these are reciprocal lattice points in a Brillouin zone. I know these are again jargons, but you can represent the crystal structure in real coordinates, Cartesian coordinate, but you can also represent in Fourier space. And in Fourier space they have very uniquely identified point like 0, 0, 0, 0.555 and so on, which has very special behavior, and that's where the band open and band close and stuff. So that's why people plot band structure on the special points, and for each lattice system this is well defined kind of. So that's why we are plotting gamma, x, omega, k, l. It's like a path, and you see this because this is a metal, there's all bands are overlapping. If silicon, there will be like a band gap and stuff, and you can do this using RPS measurement to get actual experimental band structure. It is possible. So these are densities, electron densities. You can plot it using Plotly, I believe. You can see nice pictures for thesis. All right. So this is electron density. How to go down? Is this it? Oh no, it's more. Yeah, here you go. Yeah, so another test is stress strain curve. So here what we will try to do, we will take the equilibrium aluminum structure that we got from the optimization, and then we will have strain, uniaxial strain. So we will define uniaxial strain. Yes, I don't know why I call it strain. It should be called strain, okay, not stress. So we represent strain by, strain is a tensorial quantity, you remember, 3 by 3 matrix. So only the x part we will increment from 0, 0.05, 0.1, 0.15 and so on. We increment it and calculate the stress from DFT, and then we can plot it using, I am not going to run this, but you can run this. It will look like this, and you might have seen this kind of behavior, yielding and all this kind of thing, yield point and stuff. Again, there are a lot of approximations here, but because we don't have dislocation so much, but it gives you the point where there's a elastic part, plastic part and so on. And if you can fit a straight line, y2 minus y1, x2 minus x1, remember, that will give you the C11, lattice, elastic constant. And because we are varying only in x direction, we get C11. If you vary it in y direction, like here, we will get C22. Here it will give you C33, right? And in this way you can get the entire 6 by 6 tensor of elastic constants. You can also fit the equation of state, where you have an equilibrium crystal, you try to expand it uniaxially and uniaxially contract it, and that will, the data that you get, you try to fit equation of state, kind of fit a parabola to this, and there is an equation called Birch-Murnaghan equation, and you can fit that equation to get the bulk modulus, like 79 GPa. Yeah, these are decent example. I think I give an exercise that do this same for silicon, and tell me what's the bulk modulus, C11 and density of states. Pretty easy exercise, I feel like, right, for grad students and stuff. I mean, but if you have any question, feel free to email or ask Rohit or something. All right. So any questions so far on this? Yes, please.
For a given metal, can we predict which is the best crystal structure using this solver?
Best crystal structure.
For example, why aluminum takes only FCC,
Mm.
whereas iron takes
BCC.
FCC.
Yeah. So one of the way to do this is you consider all the possible cases, BCC, FCC, HCP, and see which has the lowest energy. So that will be your most favorable energy. So that's one way to do it. Yeah. So when we do actually machine learning fitting, so that's what we do. We take aluminum in different phases, and then calculate energy and forces. Just squash all the data in machine learning framework, and then you have a model that can predict aluminum in different phases. That's all what it does.
So does the database has any data on alloys?
Oh, of course, it has a lot of alloys and stuff.
Any high entropy alloys as such?
High entropy maybe less, because there are other databases I feel like, but it becomes so difficult, 5, 8 elements and stuff. Yeah, I don't think many databases have high entropy alloys. So it's a good research problem. Make a database of high entropy alloy. Yes, disorder is there, and representing experimental system is hard. Like you want to model experiments, right? So what will be a good composition? Because even experimentally, it's hard to find out what's the structure of the system. Like if you see the X-ray diffraction of the X-ray diffraction of a high entropy alloy, it will look like an amorphous system. Anybody can tell me why? For a high entropy alloy, it will look like an amorphous system.
Because the peaks superimpose and it becomes apical.
Exactly. So there are so many small bond lengths, so many range of bond lengths between all these possible elements. It will it's very hard for XRD to find these differences, and then it will look like a large peak. So people do a lot of like right weld refinement and stuff like this to get like more precise bond length of different element types in a high entropy alloy and stuff. Very difficult topic. And I know people send the sample to a very sophisticated lab to get the composition and structure.
I read about this
SQS is a good, yeah. So SQS is a approximate technique. It's called special quasi-random structure. So what you do is you try to make a random. What you do is you take all the possible phases like FCC, HCP, BCC as a starting point, and then you take certain part of it and kind of combine it in a special way, okay, and do it multiple times in a way that the energy again the energy error start decreasing. After that, you don't need to add more structure, and then you take that and fit a Hubbard model or something like this, and that model can predict energy for any crystal now. Now once you have that, you can do this for molten substances, different phases, and that's how you get like thermodynamics. From thermodynamics, you can do Monte Carlo to get kinetics, and from there you can get the phase diagram. So that's how you get the phase diagram from SQF plus DFT. But SQS also has certain limitations. I think for disorder case it becomes challenging. When you have a lot of atoms, it becomes challenging. So there are certain other methods like genetic algorithm. There is like based on what's called minima hopping and stuff. There are several methods, energy based methods. Genetic algorithm is a very good one, which I like actually, where you take atoms, start combining them, they have a generation, offspring, another generation, keep doing it until energy converges and stuff. So that's another way to generate alloys and stuff from parent system. There are another method called that I'm very excited about, which I'll talk about on the third day. It's called Atom GPT. So here I will say that this is the property, this is the element composition generated with the crystal structure. I don't want to do all this Bayesian optimization, genetic algorithm, SQS, just generate with this. So that is the idea of Atom GPT. Just given the property, give me the structure, inverse material design. So I haven't tried this for alloys actually, so it's a good application we can think of. But yeah, I don't know, I'm just talking. Analyzing data. So once you have done this for many materials, you can make a database, and we have I think 15 or 20 database like this. So in Jarvis tools, there are a database like Jarvis DFT, AFlow, Alexandria, C2DB, CCCBDB, crystallographic open database, M3net database, materials project database, Maxine database, polymer database, protein binding database, what is this one? Quantum metal organic framework, superconductor database, this is catalyst database, vacancy database, many databases are there. So this is an example of how to get Jarvis DFT dataset, but you can use the same format to get anything else. So you install pip install Jarvis tools. So one interesting thing, let me talk about this while it's installing this. So all these databases are hosted in a platform called Figshare. Have you guys heard of Figshare? Anyone? Yeah. Figshare it sounds like sharing figures, but it's not just that. It can share a lot of research data. So anytime reject all. Anytime you upload a large amount of data, you can upload there and give you a DOI. And the good thing about this one is you can also count how many times you are downloaded. So mine was downloaded 1.5 million times. So whoever is doing this, doing a great job. You can. That's how you get credit for your research. And this is kind of data I show to my management to get funding. So so anytime you do a database or research paper, upload it to like Figshare or Zenodo is another one. There's few more like Mendeley stuff. I forget the few more, but I have put a lot of data on Figshare, and all of this Jarvis tools has linked to Figshare links. So when I ask from Jarvis database Figshare get data, and DFT3D is one of the databases I showed you. Remember? Yeah. So this was the databases. So this is one of the database called DFT3D, which has 75,000 materials. So I ask it to download all the DFT3 database and all the DFT 2D database. So you see download from that, and anytime you download this, I get +1 download there automatically.
So what is the link for the database?
It will automatically get it. You don't have to worry. So once you have Jarvis tool installed and you just ask this, it will automatically get the link and download, unzip everything internally, and load in a pandas format. So you can see there are 75,000. It's an array, 75,000 materials, and here 1,100. You can convert into a pandas data framework that we talked about it, and because we have pandas, we can see what are the columns. So we have like Jarvis ID is an identifier of the material space group, formation energy, band gap, elastic tensor, I think like 30 properties, power factor for thermoelectric properties, piezoelectric constant, thermoelectric constant, I don't know, kappa I think is, what is kappa? Thermal conductivity, yeah, thermal conductivity, band gaps, Poisson ratio, electric field gradient, superconducting transition temperature, I don't know, a lot of stuff. And you can count, it's not, some of them are very challenging to get, like superconducting transition temperature. So you can see which data is available for what. The solar cell efficiencies for 10,000 materials, formation energy for all the materials, and so on. So you can count it like this. And as a good materials informatics, you should always do something called EDA. So data analysis, effective data analysis. So we'll show you how to do this. First, we'll doing some filtering. So give me all the materials which has aluminum and oxygen from that data set using command line. So it's doing this, and you can see there are how many entries? 35 such entries, aluminum, oxygen. Give me all the materials which have energy above hull less than 0.05. This is a kind of a metric for thermodynamic stability. 0 is stable and above 0 is kind of non-stable. 0.05 is relatively stable. So 53% of the materials are thermodynamically stable in this database. Now, before we do any machine learning or anything like this, what I ask my students to do is this kind of bar plots or histogram plots. So it shows you the range of the data. So for example, bulk modulus varies from 0 to 200. So and with a peak around I don't know 80 GPA, right? So if you did not have any machine learning model, and if I had to ask you what's the bulk modulus of an arbitrary material, what I would do is just take an average of all this data, and this average will be one of the model prediction, average prediction. And any machine learning model should be better than average model. If it's not better than average model, there is not point of doing any machine learning. Does it make sense? Yeah, it's called baseline model. So it's good to have this kind of chart, histogram chart, to get like the initial idea. We are doing this for a lot of properties. If you know about electronic band gap, we talked about it. There are some DFT functional which are better in band gap from one to other. So we are seeing here MBJ band gap versus OP-BAT band gap. Don't worry about it if you are not familiar with this. It's just saying that MBJ give you better band gap. It doesn't underestimate band gaps. And you can do a lot of filtering. For example, give me all the material which has a band gap this, SLMA this and stuff. And I have seen literally people doing papers on this. They just do some kind of filtering, can get some paper, get some materials, do some more sophisticated DFT calculation, and there's a paper. So people do, and it's actually a good way to discover new materials. 18,000 cubic materials, and similarly you can do for 2D materials. Recently, there has been huge interest in this Alexandria database with around 5 million structures. 5 million structures. So you can download all of that in using this Jarvis tools stuff, and do a lot of analysis. But I would recommend start with the what is it? Hull, convex hull or something it's called. Yeah, this one. LXPB hull, 116,000 materials. These are all stable materials, so called thermodynamically stable materials, and then you can do some analysis. I think Google made a big news about this. Oh, sorry, good point. Yeah, Google made a big news about this. They discovered 300,000 such convex hull materials using all the possible YouTube time, Gmail time, all this kind of computer resources. So yeah, there's a big rush about finding new materials and material discovery. Okay, so I'm going to close this. I hope you guys are not just listening to this and actually running this. And if you encounter any problem, feel free to stop me. Okay, so one last notebook I feel like is Jarvis lamps, which is what? FF1. Okay, so this one. So in this example, we try to install LAMP software first on Google Colab, and then run for aluminum something to get energy and forces and stuff. So we will try to get lamps from GitHub repository. How many of us have used lamps before? Please raise your hand. Wow, a lot of you. Yeah. So you know the pain of installing lamps on different GPU, CPU servers. So we will be installing only serial version here, no parallel version. Yeah. So we will just run it, but once the software is installed, we will need potential. So this is one of the potential called Zhao potential for aluminum, and in lamps there is. Let me show you this quickly while it's installing the software. This is the input file of a lamps script. So let me make it bigger. So for example, to get elastic constant, what we will do is we'll take the system, perturb in XYZ direction, and in a way that is symmetrically distinct, and from there we can calculate C11, C22, and so on. And I think it will be in EV per angstroms, then it will convert to GPA or something. So this is what this code does. You first download one of the potential from Jarvis FF, and then take this in elast.mode is just a template file, and get the aluminum atomic structure. So one way to get atomic structure is POSCAR file and stuff, and also you can get the atomic structure just based on the Jarvis ID. So give the Jarvis ID, it will give you atomic structure. Get the conventional structure, and just tell it like where the executable and stuff are, where the executable of lamps is there, and from there you can just run a lamps job, and then it will give you like energy, structure, forces, and from there you can do multiple analysis. I didn't do too much, but we had done this kind of calculation where all possible known force field, all possible materials kind of hybridize, kind of Venn diagram, and calculate all possible properties like C11, phonons, thermal conductivity, convex hull, all in automated way. Like one single button and everything will be done automatically. Do the analysis, make the website, put in a website. So all this can be automated. Yeah, this is just an example. And I'm again right on time, so still running, but you can. I would encourage you to run all this example that I mentioned, just to get familiar. Yeah. Any questions so far? I know we are running a little bit fast on this last part. So what we do, suppose you have a question or request, you just go to issues and new issue that request it, and then our team will look into it and start working on it. Yeah. So with that, thank you for your time. I really enjoyed it. Hope you enjoyed it too. So we'll have few more days to go. See you again. Hopefully not. Hope to see at least some of you.